Okay, let's take a look at a few examples of how to simplify expressions that involve radicals. Of course, before we begin, let's remind ourselves of a few properties of radicals that may be helpful. First off, of course, is the nth root of x. That's the same exact thing as x to the 1 over n. So we can use that to translate from radical form, if we wish, to an exponential form. Likewise, the nth root of x to the m is the same thing as x to the m over n. Again, we can use that to translate back and forth between radical expressions and expressions involving exponents. One very useful property is if you look at the product of two nth roots, say the nth root of x times the nth root of y, that's the nth root of the product. And this can be used forwards and backwards. If you see the nth root of a product, we can break it apart into the product of two nth roots. In a similar manner, the quotient of two nth roots can be written as nth root of a quotient. And again, that works both directions. If we see an nth root of a quotient, we can break it apart into a quotient of two nth roots. Okay. One more detail, and that is if you're taking the nth root of x to the n, remember that that equals x if n is odd, but when n is even, we have a little bit different behavior. Suppose your x value is a negative, n is even, that's going to make x to the n positive. Then you're taking the nth root of a positive value, which you should get a positive value out as a result because we're talking about a principal nth root. And so, of course, what have we done to x, which was originally negative? Well, we made it positive. If we had started with a positive x, it would have also been positive. So it looks like we're taking the absolute value of that original value of x when n is even. Okay, so kind of keep those in the back of your mind as we work through these next several examples. All right, so example 1. Okay, let's simplify the fourth root of 32 x to the 6th y to the 8th. Okay, now how can we do that? Well, what we'd like to do is to break this apart, right? We have a fourth root of a product, just like an nth root of a product over here. We'd like to break that apart into a product of a bunch of fourth roots, where as many of those fourth roots as we have are fourth roots of perfect fourth powers. Okay, so first step. I've got x to the 6th here, I got y to the 8th here. I'm not sure exactly what this 32 has in it. Let's consider the factorization of that. 32 is the product of 5 2's. So let's rewrite this as the fourth root of 2 to the 5th times x to the 6th and y to the 8th. And then, with that intent to break it apart into the product of 2 or more fourth roots, where as many things as possible are perfect fourth powers under one of them, look, you've got 2 to the 5th here. That could be split up into 2 to the 4th times 2. 2 to the 4th, of course, is a perfect fourth power. This x to the 6th, that could be split up into x to the 4th, a perfect fourth power, times whatever's left, x squared. This y to the 8th, that already is a perfect fourth power. I'm going to put the whole kit and caboodle right there. Of course, that's the fourth power of y squared. Okay, so I can rewrite this fourth root of all this mess as the product of 2 fourth roots, like that. This, of course, is just 2x y squared. Each one of these guys is a perfect fourth power. This, I just can't do much with. So I'm going to leave it alone. And that is my simplified version of the fourth root of this product. Okay? Okay, let's take a look at another example here. Number 2, suppose we wanted to simplify the quotient of the fourth root of x to the negative 3rd over the fourth root of x to the 9th. Okay? Well, we have a quotient of 2 fourth roots, just like a quotient of 2 nth roots here. We know we can rewrite that as the fourth root of a quotient, namely x to the negative third over x to the ninth, the question is, does that help? And yes, it does. What it does is it allows us to focus our attention on this x to the negative third over x to the ninth, with this fourth root kind of being moved out of the way. We just now have to simplify an expression involving exponents here. Okay, a couple different ways you could do that. Of course, you have two different powers, the quotient of powers with the same base. We could subtract the exponents. We could write this as the fourth root of x to the negative 12, right? Negative 3 minus 9. Of course, we'd have to turn right back around and maybe write that as 1 over x to the 12th under the fourth root. Okay. Alternatively, you could bring this x to the negative 3 down as x to the positive third and then add the exponents. You get the same thing either way. Okay. The fourth root of 1 over x to the 12th, is that any better? Yes. Right? We have the fourth root of a quotient. We can go right backwards to where we began, really, and talk about the fourth root of the numerator over the fourth root of the denominator. But in this case, those are nice things, right? The fourth root of 1 is just 1, and the fourth root of x to the 12th is what? This is x to the third. You got to be very careful here. It's sneaky. This is actually the absolute value of x to the third. Remember, the fourth root is going to be a positive expression, right? And had x been a negative, x cubed might be negative. Okay? We're really seeing an application of this down here. All right? But if you just remember, anytime you take an even root, you have to end up with a positive value. You can use that to determine when you need to put in the absolute values or not. Okay? So be careful there. That's sneaky. All right? Okay, how about this example? Number 3, the fourth root of 2 to the fourth over x to the 8th times y to the 24th. Okay, this one's actually a little bit easier, I think. Notice what we have again, a fourth root of a quotient, just like an nth root of a quotient. We can rewrite that as a quotient of two nth roots, just like in the last problem, only going the other direction initially. So this would be the fourth root of 2 to the fourth over the fourth root of x to the 8th and y to the 24th. Look down here. We have a fourth root of a product. Nth root of a product could be written as the product of two nth roots. So I could write this as the fourth root of x to the 8th times the fourth root of y to the 24th. And that's still sitting under the fourth root of 2 to the fourth. Okay? Now, in all actuality, you probably wouldn't write these two steps because look what we have here. The fourth root of 2 to the fourth is just 2. And you could see that even over here. The fourth root of x to the 8th, that's just x squared. And again, that's something you can see right here. As long as everything in here is multiplied or divided together, we can get away with that. The fourth root of y to the 24th, likewise, is y to the 6th. Okay? No radicals were left. That's it. It's simplified. Okay? All right, how about another example here? How about the cube root of the quantity x minus y squared times the fifth root of the quantity x minus y to the 8th, all of that over the square root, remember we don't have to write the 2, of the quantity x minus y to the third. Okay, what should we do here? Well, we've got a product of some roots, but notice they're not the same root. Right? So I can't play this card. Okay, not yet. And I've got, likewise, a quotient of some radical expressions. But again, the indices here, the 3 does not agree with the understood index of 2 here, nor does the 5 agree with this. So I can't play this card yet. Right? What I can do is play this card, use this property. We could rewrite this in terms of exponents. This first guy right here, x minus y to the second power, and then we take the cube root, that's the same thing as x minus y to the 2/3. Again, appealing to that property. And then here, in a like manner, we have x minus y to the 8/5. And finally, in the bottom, we have an x minus y. Again, remember, this is an understood 2 right here, to the 3/2. Okay? Now the laws of exponents take over. We know exactly how to deal with this. We have the same base to various different powers being multiplied and divided. Okay, so up top we need to add those two exponents, which will give us x minus y to something, to some sum. And over that same base to another power here, we've got to subtract this exponent off, right? So putting that all together in one fell swoop, we'd have x minus y to the 2/3 plus 8/5. That's what the numerator would be. But then when we account for the denominator, we need to subtract off 3/2 from that. Okay? Now, it's a bit annoying here. We had to get some common denominators to crank that expression out, but it's not too bad. X minus y to the, what do we have here? 20/30 would be 2/3. 48/30, that's what we would need 8/5 to be to get a common denominator of 30. And then finally, minus 45/30. Okay, which is just x minus y to the, let's see, 48 minus 45 is 3, 20 and 3. It looks like 23/30. Okay, that's our answer. Now, it is, I suppose, worthwhile to note, we've given an answer involving rational exponents when our problem started with radicals. If we had wanted to write this in radical notation, we can use this trick again. We can just say, hey, that's x minus y to the 23rd power, taking a 30th root of that result. Okay? So there is our simplified version of this mess. All right? Okay, let's take a look at one more example. Okay, number 5. Suppose we wanted to simplify the square root of 3x to the negative 2y times the square root of 5 to the negative 1 times x times y to the negative 2, all of that over the square root of 5xy. Okay, so here, unlike the last problem, we don't have a mixture of types of radicals involved. These are all square roots. We could combine the top together and say that's just the square root of 3x to the negative 2 times a y times a 5 to the negative 1 times an x times a y to the negative 2, all that sitting over the square root of 5xy. And then we have a quotient of square roots, which is the square root of a quotient. So that's the square root of all this mess. Okay, and truth be told, most times you would go directly from here to here. Okay, knowing that you could apply both those rules essentially simultaneously. Keeps the work down. Now the advantage to doing that again is the radical is kind of out of the way here, allowing you to focus your efforts on simplifying this expression underneath that just has exponents in it and products and quotients, and that should be pretty fast. You have an x to the negative 2 times an x to the first. Adding those exponents, you'd have an x to the negative 1. So we have a 3, we have an x to the negative 1. We have a y to the first, we have a y to the negative 2. Adding those exponents, we'd get y to the negative 1 as well. And of course we still have a times 5 to the negative 1. All that sitting over 5xy. Of course here we have a quotient of powers of x, same base. So we can subtract the exponents. We have a negative 1 up here, we have an understood exponent of 1 down here. So that's going to be x to the negative 2, which really just means you put an x squared in the denominator. Okay, so I've got an x squared down here. Likewise with the y to the negative 1. That's y to the negative 1 minus an understood 1. That's y to the negative 2, which puts it in the denominator. Again, the other way to think about this is you're just moving across the fraction bar, changing the sign on the exponent, and then they combine. The 5 to the negative 1 also comes down to combine with the 5 that's already there to give us 5 squared. And the 3 is still left there. Okay. Now, notice we have a square root of a quotient. Certainly, that's the quotient of 2 square roots. Okay. Square root of 3 is fine. Square root of 5 squared, that's going to be 5 for certain. Square root of x squared, that looks like a perfect square. It is, of course. But is it x? Well, we aren't completely sure, are we? If x was a negative, remember, this tells us we have absolute value of x there. And the same thing works for y too, right? So we have absolute value of x times absolute value of y. That's the same thing as the absolute value of xy if we wanted to write it a little bit tighter. And this is pretty tight. Okay, so there is our simplified form.